So, good afternoon, everyone. I'm Vinícius, and just a small correction is actually I'm still a master's student and on the transition to the PhD, and I'll be starting this September at Inria. So, I'm a student at Université Grenoble Alpes in France, and I'll be starting the PhD in Inria in the same city in France. And today's talk, then, it's about, as introduced, a benchmarking of fairness-aware learning on differentially private synthetic data. So I would like to start this talk by giving a small introduction and just actually a recap for most people about synthetic data, specifically how they are taught by regulators and adopted by the industry as an approach for a privacy-aware approach for sharing data access while still limiting access to the original records. The original idea, for data synthesizers is then to learn a data distribution and sample some synthetic data based on this learned distribution. However, it is important to mention that by default, there are some concerns. One, for example, is about privacy, in which we can still recover some sensitive information. And the other one is not about privacy, but rather fairness, as it has been widely shown by the literature that it can reproduce or even worse, amplify a bias that it's already originated in the original data. So how can we overcome the part for the privacy? One example is by using differential privacy, which has already been introduced in the previous sessions. More specifically, we have differentially private synthetic data generators that are able to generate synthetic data with formal privacy guarantees. And these privacy guarantees are quite interesting because they allow us to perform downstream tasks in terms of learning and fairness tasks without compromising the privacy itself. However, the noise which is introduced by these mechanisms might as well distort the subgroup structures, which would compromise then the utility as well as the fairness. In terms of the utility, it would lower the predictive performance, and in terms of the fairness, it would then amplify the group disparity. This is what we call the DP disparate impact. And more specifically, so as we have the original data set right here, it would just undergo some differentially private mechanism to generate the synthetic data set. This is no problem. Okay, good. You can use it to train your models. However, the problem is how this would reflect on the group outcome. And right here is exactly the problem that we are facing for fairness, in which it has been shown that for the majority groups, they don't actually suffer that much in terms of loss of utility. However, for the minority group, well, someone better help them because it's not good for them, right? And this disparity in performance is exactly what we are worried about correcting. So how can we measure or even correct this disparity? In terms of measuring, we can use group fairness metrics. And here I give some examples which we use in the paper. And what we do is just to collect then an utility such as the accuracy, the true positive rate as well as the positive prediction rate. And then you just compute it for both groups and take the raw difference. That is one example. And in terms of correcting, in the literature, there are different types of mechanisms, fairness mechanisms, which can be grouped in 3 different families. First is the preprocessing mechanisms, which would alter directly the training data to ensure fairness. We have then the in-processing mechanisms that would change directly the objective of the learning algorithm or the learning algorithm itself in order to ensure that the model is fair. And the third is the post-processing mechanisms that would act directly on the prediction of a trained model. So they don't care really about the training or the data, just on the prediction itself. Good. So we are already aware that there is a problem of disparity and how can we compute and maybe even correct this disparity. So what we ask ourselves is if the already studied and provided by the literature fairness mechanisms are able to correct the fairness loss caused by the differential privacy. And if it is the case, where should we intervene in the pipeline? So either in the pre-processing mechanisms or with the in-processing or post-processing to achieve the best trade-off in terms of utility, privacy, and fairness. To be able to answer these two questions, we introduced the benchmark DP Fair. This is an open source framework that we developed that allows us to test with different data sets and essentially with different DP synthesizers as well, in order to isolate the impact of both the fairness and the differential privacy in the collected metrics. So this framework is essentially is composed of three baselines. We have the baseline, which is called baseline, and this here is the untouched data training the model, and then you just collect the metrics. Okay, there is no intervention in terms of fairness or privacy whatsoever. Then we have the DP only, which the idea is to isolate the impact of differential privacy in the collected fairness metrics. Then we have the fair only baseline, which essentially only applies the fairness mechanisms, so we're not worried about privacy here. And later we have what we really are interested about, which is the relationship between the differential privacy with the fairness mechanisms, both acting together. So our experiments are composed of 3 real-world datasets, as well as 6 datasets, synthetic datasets, that we can control the bias to be whatever we want. We also use 3 different types of machine learning classifiers, each one from a different family. And we have here the logistic regression, the random forest, as well as the XGBoost, all applied with 12 different privacy budgets. And these privacy budgets were chosen to represent different privacy regimes, 20 different random seeds, as well as 2 different marginal-based synthesizers, which are the AIM and the MST. And there is something that I forgot to add to these slides, which is important to mention, which is about the fairness mechanisms. Well, in total, we tested 3 different mechanisms for the pre-processing stages, 2 for the in-processing stages, and 3 for the post-processing stages, which I'll present later with the results. And also, we decided to do 2 different ablation studies to ensure that our design choices are robust enough. However, due to time constraints, we will limit the results here and in the poster to those achieved by the AIM data synthesizer with the adult dataset. For those who are interested, we refer to the full benchmark, which is present in the paper, and there will be a QR code in the end. Good, so what are the selected results? As I mentioned, I would like to start by providing the result from XGBoost, which is the most robust classifier that we tested. It's important to mention that we tested all of the classifiers by default settings, okay? And what we can see here is on the y-axis. On the y-axis, we have the accuracy, meaning the utility, and the higher the accuracy represents the better utility. And on the 3 graphs, on the x-axis, we have the 3 different group metrics that we collect, and the closer to 0 represents the most fair setting. Yeah, and in terms of the size of the markers, what we have is that the smaller the size represents a more strict privacy regime, and the larger represents with less strict regimes for privacy. And what can we identify from this is, well, if we look at the graphs specifically for the EOD and the SPD, is that the DP fair settings, they're always going towards the 0 compared to the X markers, which is the DP only. This demonstrates that even though we have the differentially private setting, we're still able to correct the fairness. There is indeed a loss in terms of utility. However, we can still keep this utility, although we are bounded by the loss provided by the differential privacy. And well, this could be, as I mentioned, an artifact of the XGBoost because it is a quite robust classifier. So what we did was then to select a set of representative fairness mechanisms for each intervention stage and plotted for all different set of classifiers. And what we're still able to identify is that for all of the different classifiers, the trend still remains the same. When we apply the fairness mechanisms, we're still able to go towards the full the fairness 0 point in the graphs, indicating fairness. So this indicates that the trend will keep happening towards different set of classifiers. So it's not an artifact of how robust was XGBoost. Good, so overall, what can we conclude from this? is that, yes, we are able to correct the fairness, even though on a privacy setting. However, this is only partially correction, right? And it is also metric dependent. It doesn't happen that if you correct one metric, it will also correct the fairness for another different metric. And overall, the post-processing stage was actually surprisingly the most stable and the strongest option for selecting to intervene in order to achieve the fairness. And here we selected the ROC and the EQ odds mechanisms as the strongest choices, because they were the most stable with the most, while keeping the strongest correction in terms of fairness. However, we still have some remaining options, some remaining questions, which concerns about, for example, the binary tasks. In this paper, we only evaluate binary task classification. So we would recommend extending this framework towards a multi-class classification. We only test a simple protected attribute. So we would recommend extending this to multiple attributes and more complex protected attributes. And we're also aware throughout the research that there exists synthesizers that generate both fair and private data sets. So what we do is recommend extending towards the relationship with them compared to the overall fairness mechanisms. And for that, we released the full benchmark open source, and it can also be tested by just installing via pip. Thank you.